little class. Okay, we're going to talk about another very important application of magnetic fields, and that is a device called a cyclotron. And so basically what we have is we have two objects that are called Ds because, well, they're shaped like the letter D. And let's say we put a charged particle in the middle of that. So we have some source of charged particles. We place it in the middle. And let's say we take this plate here. Say these are metal devices. They're actually, see if I can find a good picture of it. They're three-dimensional objects. So I should have had this picture open earlier. Well, see, I'm just going to hold this picture up. So yeah, those D's are hollow inside. And so you've got, like the particles can be in between the two plates. So completely hollow inside. And let's say we apply a positive charge to one plate and a negative charge to the other plate. And so that'll create this electric field. Now, kind of have to consider which type of particle we're dealing with here, if it's a positive or a negatively charged particle. Works the same for either. Let's say that this is an electron. So it's going to accelerate over to here. And say we have a magnetic field that is perpendicular to the board. And so remember when you have a particle moving in a perpendicular magnetic field, it goes through circular motion. So let's look what happens, just like we talked about the mass spectrometer, it's kind of that situation here. There's a magnetic field into the board here, and so that's going to cause the particle to go through this circular motion. Actually, I want to make this a smaller circle. Yeah, let's say it goes through this rather small circle. So say we have a strong magnetic field here. And now it looks like it's about to hit a wall because now it's back in the gap. There's an electric field. And if this is a negatively charged particle, the force is going to be in the opposite direction. So imagine in the time it took for this particle to make this half loop here. Let's say we switch the charges. So now it's positive and negative. And so the electric field reverses direction. It's now when it reaches this gap, instead of hitting this wall, it's going to accelerate. And then it's going to enter the region with a magnetic field again. And it's going to go through a loop. But now because it accelerated, it's moving faster. And so it's going to go in a bigger loop. But now it's, reached, now we have that same problem as before, where again, remember this is a negative charge, so as soon as it hits an electric field like this, it's going to start slowing down. But we reverse the electric charges again, so we reverse the electric field, and we cause it to accelerate again. And so you can kind of see how this device is going to work. Every time it goes through, it's going to be going faster. And eventually we'll kind of run out of room. Maybe we'll just, once it kind of reaches the outer radius of the device, then we say it goes, we just let it go flying off through like a hole in the device. And let me show you a picture of that. It's actually a really cool picture. It's on the same page as the other one. So this is an actual cyclotron. That's what this device is. And you can see this beam here. These are the charged particles. They're so energetic, they're ionizing the air and creating a visible beam. Now, one minor issue here, we have to keep reversing these electric fields every time it, makes half of a loop. And it's, speeding up every time. The radius is increasing every time. How can we ensure that we're actually going to be able to reverse these? And so let's analyze what happens when this charged particle enters the region with a magnetic field. Like this region in the D's. And so there's a force on it. Let's just apply Newton's second law, F equals ma. Now the force is going to be QVB. So again, magnetic force, sine of theta. But remember, the magnetic field is perpendicular to the board. The velocity is always in the board. These two are perpendicular to each other. And because they're going through circular motion, the acceleration is v squared over r. And let's look at the time it takes to go, like say, pick this one here. It goes a particular velocity. Like every arc is going to have a different velocity. Let's just pick one. We know that it's going to go through half of a circle. So the distance it travels is pi times the radius that it's at. And that would be equal to v times the time it takes. So t, let's call it delta t. So delta t is the time it takes to go through half that circle, and then it accelerates again, and then it goes onto a bigger circle after that. And let's actually solve for delta t. So this would be pi r divided by v. Now, we're going to have an annoying square root here, it looks like. Oh no, we're not, because one of these v's cancels out. So let's take this equation. Let's solve for 1 over v. So 1 over v, we bring that over here. That would be m over r. So we divide this v out, so that's over here now, so we have m over r. And then we have to divide by qb to get v by itself, or 1 over v. And so if we just plug that in, delta t is pi r, pi r, and then times 1 over v. So we have m divided by r qb, or delta t is equal to pi m divided by qb. See, something very nice happened here, and then as the r's canceled out. And so, the time it takes to complete its journey through one of these d's is independent of the radius. And that's what makes the cyclotron possible in practical terms. Because you can just calculate delta t. So if you know the mass of the particles, you know the charge of the particles, or if we just saw, like if we're using electrons, you don't even need to know those individually. We know that ratio for an electron. And B is the magnetic field, which is something you create when you're designing the experiment. And so delta t is just a fixed number for any particular experiment. You have a particular particle of mass m and a charge q, fixed magnetic field. And so delta t is going to be a fixed value. And we're actually going to learn later. But the idea, you can have this electric field kind of switch back and forth in a very predictable manner. And again, this isn't something we talked about in this class, but it's a term I'm sure you're familiar with, and that is alternating current. And alternating current is not something exotic. It's something that you've, if you plug something into an outlet, you're getting alternating current out of it. So it's something very well understood. We can create like potential differences or currents that vary in a very predictable way. So they have a fixed frequency, and so you can just hook this up to a source of alternating current and get these positive and negatives to switch however you like them to. And so that's what makes this device possible. And basically what this is this is one of the first kind of large-scale particle accelerators, because it speeds up every time it goes through one of these gaps. And by making this bigger and bigger, you can keep it circling for longer, and it's speeding up every time it completes one cycle. And so it seems like the only limitation is the size, because the radius has to keep increasing. However, there is another fundamental limit to the cyclotron. And that is, this analysis here is actually not 100% correct. Like just starting here with F equals ma. And the reason why, this is Newtonian mechanics that we're using. However, at high speeds, Newtonian mechanics kind of breaks down. And so this very predictable delta t being a constant, that only works for speeds much lower than the speed of light. Once you start getting close to the speed of light, even like 1%, or even a fraction of a percent, you'd start noticing differences in delta t. So yeah, just F equals ma does not apply there anymore, and you have to use the rules of the special theory of relativity. And basically what the theory of relativity did is just replace Newtonian mechanics. There was like a fundamental flaw in the assumptions that Isaac Newton made, and that Einstein discovered. Now, something, I've read a little bit of Newton's direct stuff. It's very difficult to read, but one thing I found fascinating is this assumption I'm talking about that Newton made that was flawed is something he specifically wrote down in his book. Basically, he described time as just something that happens the same everywhere in the universe. What Newton said is time works the way we intuitively think it would work. Like, say 5 seconds pass here, well, 5 seconds is going to pass somewhere else as well. It's not going to depend on any other factors. That's something so obvious most of us wouldn't even question it, but Isaac Newton did. I mean, he was aware that this was an assumption, so I was very impressed with that. Even though it was wrong, just the fact that he recognized that this was an assumption, I always found that very impressive. Newton was a pretty smart guy. All right, so just another application of magnetic fields. So I think that'll be it for this video.